Okay. So the plan is to kind of give you a high-level idea of what we are working on and give you a teaser for one of the problems. So I'm not going to go into details about lots of things, except for the last problem. I'll kind of motivate you, and hopefully you'll come and take my 171, and then you'll learn all more about this. Okay, so this is work that was done with my longtime colleague, Divi Agrawal. He's another professor at UCSB. None of you have taken my class, yeah? No, okay. I'm teaching 138 now. And three other students, there's Mohammed Amiri, Sujaya Maya, and Victor Zakhari. Victor was actually moderating the panel on the other side of the wall. Okay, so let me give you, how many of you have studied databases? A basic database class, 170A, 4A or something. Okay, if you haven't, it's okay. I'm going to summarize 140A in 3 slides. It's a fairy tale. Basically, we are told that data is all relational, it's very structured in tables, it has columns, it has rows, it has attributes, it has a primary key, everything is wonderful, everything is very easy. You can ask your question. There's Victor. So a lot of the work I'll talk about is some of his work. So this is part of the myth that we teach you in class. We also assume data is all very clean. If you have my name, El Abbadi, I always have trouble with it. Does it have 1 B or 2 Bs, 2 Ds or 1 D? Does it have an L? Is L part of the last name or is it part of the first name? Or is it the middle name? I get it. So every table has my name in a different form. This means data is not clean. But we assume data is clean, there are nice schemas, everything is very elegant. We also have been living in a world where we assume, this is maybe a decade ago, assume that the machines were sitting in engineering 1 before it was recalled HFH, and we knew who worked in these machines, we trusted them, we knew everything about it. And failures were very simple. Yes, there were failures. The world was not completely easy, but if a machine failed, it just crashed. It stopped working. It didn't do anything bad, it just stopped working. So you have a machine, either it's up or down. And then in the last 5, 6, 7 years, we've had this big tsunami. A whole complete change in the world has happened. Turns out that data is not structured. We have lots of very interesting types of data. We have images, we have sensor data, we have videos, we have all kinds of stuff. So we have to understand how to deal with these different types of data that might not understand, God forbid, SQL. Yeah? So be careful. The data is not clean. Like I told you, we are accumulating data from all over the place, and even if I am trying to do a benign SQL query like a join, I still could have problems because my data doesn't, the same attribute, the same person is not referred to in the same way in both tables, for example. So we have to clean it. And the big thing that worries me most of the time is that failures are no longer just crash. We have malicious failures. This is a big issue that I am giving my data to people I don't trust. I don't know if the code has bugs. They might be malicious. They are not trustworthy. There are all kinds of things where the same program, the same process might answer yes to me and no to vector at the same time. So this is an inconsistency that arises. Often we call this Byzantine failures. A Byzantine thing is a bad thing. Yeah, it's like tries to do something bad. So this has been in the news recently a lot. So there have been all these data breaches that have been happening. Facebook records leaked a lot of information. 450, 500 million Facebook records. That's a lot. That's more than all the people in the US. And it's not only that there are leaks, but there could be sabotages of the data. We are afraid that the data itself could be messed up, could be changed intentionally, could be maliciously changed. And in fact, James Clapper, who was the head of the FBI, said that we expect the biggest problem to be data manipulation in the future. This will be a threat to us. We are not just afraid of leakage, of information going away, it is that somebody maliciously tries to change the data. So this is what we are trying to do in DSL in our lab, is to address these kind of environments, how to deal with it in a big sense. And we focus on two main problems. One of them is data in the cloud. So how to manage data in a consistent manner, fault-tolerant manner, scalable manner, all of this, as well as blockchain, which brings me to the reason I'm here. 5 years ago, I was still only working on cloud management. But blockchain actually is also a very scalable, large-scale system which we would like to deal with and manage in an environment where we don't trust everybody. So there's a problem. Help. What are we going to do? Does anybody recognize this? No? Yes. The Beatles. Okay. Luckily, we have the infrastructure to help us address many of these problems. And luckily, if you are especially at UCSB, we have several courses that lay the foundations for this. There's obviously a lot of work in cryptography, in security, but there's also a lot of work in distributed systems. Distributed systems has been addressing the problem of storing or managing processes that are distributed in a large system in an environment that can be malicious. It could be crash only, but could also be malicious. We also have a lot of work in the database community that basically addresses the problems of how to manage data in a distributed system. So distributed databases. So there's a lot of stuff that we can learn and that can help us develop things. And the nice thing is that often these results are 10, 20, 30 years old, and at the time when they were proposed, nobody thought they were relevant. People thought, why are you doing this? And in fact, now it is becoming obvious. And so it is good to doing research because we speculate about the future. And luckily, we can take results from the future and apply them to things that are happening now. So I want to just mention two particular protocols. I'm not going to give the details, but that are especially relevant in the context of large-scale distributed systems. One of them is atomic commitment, where you have multiple sites that store the data, and you're executing a transaction that needs to transfer $100 from my account to your account. These are on different machines. I need to make sure that even when there are failures, and the traditional approach was to assume that it was crash. Yeah, so crash, I don't know what this hashtag is, but so if there are crash, I want to execute this consistently, correctly, even if there are failures. So there is a commitment protocol, and it's called two-phase commit, and it's a very elegant protocol. Another protocol that deals with how do I deal with failures? I have my data, it's sitting on a machine. This machine can crash, let's assume. If it crashes, I cannot access the data. So what do? I have another copy. I put it on another machine that hopefully is not sitting in the same rack, in the same data center, maybe a geographically place that is far away. So that if one crashes, the other one does not crash. So that is replication. So replication, there are lots of techniques that have been developed for that, and the most famous is one protocol called Paxos, which is developed for crash failures and maintains replication. And if you know anything about the Google file system or Bigtable, it's basically at the infrastructure of the Google infrastructure for managing data. So they are using Paxos. Okay, the problem is, and this is where we stand now, is that this assumed that we know who is part of this system. I know that I have my data, it is replicated on 3 sites, I close the door, nobody comes in, nobody comes out. Is this realistic? No. We have a whole bunch of people who joined us after I started the talk. Did I kick them out? No. I was happy that they came. More resources is a good thing. So the question is, how do I have a system that is flexible, that does not depend on knowledge of the exact number of people? Why do these Paxos protocols or these consensus protocols need the number of people? Because they are basically based on the assumption of we're going to agree on something if I have a majority, if I have a quorum. This is how we elect a president in this country. How do we elect a president? We do a census. The census actually has been a big issue in the news recently because you really need to know exactly the number of people in this country so that if we say half of the people plus one voted for Trump, then he becomes the president. This is not how it works, but that's what ideally happens in a democratic system. So the problem is, and you are all familiar with blockchain, we don't know who the participants are. So let me go to blockchain. Blockchain started by saying we are not going to use the traditional approach of banks. So if I have a bank, I have money, I give it to the bank, you have some money, you give it to your bank, and our banks negotiate with each other and transfer the money. If I want to give you $100, the bank probably doesn't actually give my bank doesn't give your bank $100. They write in their ledgers that we owe $100 to that bank. And then hopefully over the end of the day or at the end of the month or at the end of the year, we will figure out how much you owe me and how much I owe you. So instead of this, what blockchain does is it says, let's remove these trustworthy entities and replace them with everybody. Everybody around here is going to be part of this. It's a peer-to-peer network that is communicating with each other, and we don't have one trusted entity, a bank, a big solid stone building, but everybody. Do I trust everybody in the room? No, I don't know everybody in the room, but I think I know that most of you are probably good people, 51% of you. So what does blockchain do? I don't know why the fonts have been messed up like this, but basically let me skip this. So basically we have a blockchain, which is basically a linked list. Yeah, you all know linked lists, and you have pointers between them. And then the big challenge is this would work in the environment you are used to, which is a crash environment. Yeah, a machine, we have pointers. I trust everything is correct. The problem is that if I have malicious failures, if I don't trust whatever node is having some of these blocks. So instead of that, we do this idea of hash pointers, and you probably have heard more about this. So this is how we achieve tamper freedom in that environment. Now that I have a linked list, what do I do with a linked list? What do I do with a blockchain? I usually want to add a node to it at some point. Yeah, that's the whole goal of this. So the big operation is how to do an insert operation. And insert is really going to be among all of us. We all want to add. I want to add, you want to add, she wants to add. So what do? We have to all agree on one of us only adding. That's the consensus problem. So now I would say, could I use Paxos? Could I use any of these Byzantine Agreement Protocol? And the answer is no, I could not, because I don't know the number of participants. So this is the nice intellectual challenge that blockchain is posing to us as researchers, is how do I solve the consensus problem in this environment? And there are lots of attempts that have been made to try and address this. And this is where the world of blockchain partitions into two parts. There is the permissioned and there's the permissionless. The permissioned is a more traditional approach. This is database people like me who said, okay, I like the idea that I have this blockchain, which gives me provenance, which gives me where the data came from, it gives me the history. There are all these nice things about it. But I am living in a closed world. But I don't trust everybody. So this is where we have a permissioned blockchain, is where I'm going to have a blockchain and I'm going to use a consensus protocol, but instead of using the Paxos, or one that assumes crash failures. I'm going to develop protocols, and there are protocols for Byzantine fault tolerance, which is basically ones that assume malicious failures. So that's the permissioned world. So the famous protocol is practical Byzantine fault tolerance, which is due to Castro and Liskov. Barbara Liskov got the Turing Award for this, is among the work that she did. And then there's the permissionless world, where it's all open. Each of us tries to mine, and by mining, I'm really replacing communication with processing. So instead of going out and talking to people and getting a majority or two-thirds to agree with what I want, instead I'm going to work on a hard problem by myself, and if I solve it first, I raise my hand and I'm the winner. This is kind of the trade-off. Of course, this requires a lot of energy, and there are all these problems with it. Okay, so let me give you, so how much time do I have? When do I end?
You've got another 10 minutes to talk.
Okay, so I'll give you a high-level idea of what we're doing with permissioned blockchain. So we have lots of projects in our lab involving permissioned and permissionless blockchains, as well as cloud. So this is the kind of the context of what we are doing. Divi, Agrawal, and myself. This is our lab's focus. So the first question is, with permissioned, so closed systems, do I have applications other than cryptocurrencies? And yes, there are lots of applications, and this is what gets database people very excited, is that it is basically a supply chain world. So this is an example of fish production. People are worried that they are eating rotten fish. Now the question is, why is the fish rotten? Did the fishermen supply rotten fish, or was there a delay in the transportation that happened? Was it stored in the storage rooms too long? What happened? Who broke it? So there is a supply chain of lots of different entities. They need to work with each other, but they don't trust each other. That's perfect for blockchain. It gives me the history of, instead of with Bitcoin, I know the history of where this particular Bitcoin came from. I got it from Alice got it from Bob, etc. Here we know that this fish came from so-and-so and went, and we can track down everything. And if anybody lies, we hopefully can identify that liar. And so basically it gives me transparency and provenance. And one thing I need to make clear is that the traditional blockchain approach and all of this does not provide privacy. So if you want privacy, you have to work harder on it. It actually is designed to provide transparency, to give provenance. So we've been working on various projects. These involve, we have a project called PowerBlock, which basically focuses on trying to improve the performance of the blockchain. So there are famous or well-known commercial systems like Fabric, Hyperledger Fabric from IBM and other whole consortium, and it has an approach of dealing with how to execute operations, whether you execute it first, you order it first, and instead what we are doing is an alternative approach, and we show that it gives us good performance. Then I brought up the issue of privacy. Imagine now that we have various different entities, and I'm the fisherman. I have my own local stuff, but there are some interactions between me and the transportation system. So there are internal transactions, there are internal operations that are happening on my blockchain that I want to be confidential. I don't want people to know about my secret recipe. If I'm a cook and I'm developing something, I don't want this to be exposed to everybody. But on the other side, I need to expose certain things when there are cross-chain transactions. So so the Caper, we deal with that. Then we have an issue, we have another project which is dealing with scalability, which is using a standard approach in database systems and in general, which is sharding. You have a lot of data, you have a lot of processing. Instead of doing it on one site, you break it up. The problem, again, is the cross operation. So that's with Sharper. And finally, we have another project that's still ongoing and is in collaboration actually with some colleagues in France, where we are looking at crowdsourcing. So we are crowdsourcing something, and we want to maintain both confidentiality, but also verifiability. I want to be able to verify that nobody is cheating. Okay, so this was about our permission. I hope I have 10 minutes. Okay, I have 10 minutes. So I want to talk a little bit in detail to give you a flavor of the type of work we do here in our lab. So I'm going to skip this. So basically the issue is that I have lots of different currencies, potentially Ethereum, Bitcoin, etc. And I have some of Bitcoins and Victor has some Ether. I would like to exchange those two with each other. So I want to get his, we decided I'll give him 100 of mine for 50 of his, for example. So there's this agreement. So we have two blockchains, the blockchain, two blockchains, one of them for Bitcoin and one of them for Ether. In this case, Bob has X Bitcoins and Alice has Y Ether, okay? And what they would like to do is they would like to exchange ownership. So Bob would like to give to Alice his X Bitcoins and Alice in return will give her Y Ethers. So what we want to do is to develop a protocol that basically transfers the ownership from one to the other so that Alice now owns the X Bitcoins and Bob now owns the Y Ethers, okay? The animation is getting messed up during the transfer, but okay, so there is actually a very interesting protocol. This was an old protocol from the old days of blockchain. This is a permissionless system. Nolan, in a blog, basically in a comment, developed a protocol to solve this problem. It took 6 or 7 years for a computer science professor, not me, but Maurice Hurley, to say, oh, I can take the solution, generalize it, formalize it, and publish a nice paper in a good conference. So that's how things evolved. It took, look, how many years? 6 years. So the formulation I'm developing is actually basically Nolan's with a little bit of Maurice Hurley's. So how do we solve this problem? So we're going to use smart contracts. Alice is going to take her money. She wants to give her Bitcoins to Bob. So she's going to put her X Bitcoins in the blockchain with a lock on it. The lock has a hash, and the hash can only be broken if you know the secret S. So we have a X Bitcoins sitting in the blockchain, and there's a lock on it, and the lock can be broken, can be opened if you know S. S is Alice's secret. So Alice knows the secret, she hashes it, and puts the value of the hashed value on it. And she says, whoever has that value can get the money. At this point, does Bob have the money? Have the secret? No, he doesn't know it, so no, it's safe. But she's negotiating with Bob. Bob wants to help her. So what he's going to do is he's going to do the same thing. Once Alice puts her hash value on the blockchain, blockchains are visible to everybody, yeah? So he can actually see it. So he will take the string of bits without understanding what they mean and put his Y Ethers in his blockchain, in the blockchain that has the Ethereum, and lock it with H. He doesn't know S, but it doesn't matter. Who knows S? Alice. So what can Alice do? Alice can go and get Bob's money by revealing S. Once she's revealed S, what does Bob do? It's revealed. It's now public. That's the nice thing about blockchains. They are available. Everybody can see it. So Bob now takes the money and goes to, my animation is not working. Bob basically takes the secret S and gives it to this blockchain and gets the money. Okay, so what could go wrong? What could go wrong is that Alice naively agrees with Bob. I'm sitting with you, I agree on this. She puts her X Bitcoins in the blockchain, and then Bob says, goodbye, I'm not interested anymore, I'm going home. Now all her money is stuck in the blockchain. That's horrible. She loses her money, and Bob doesn't lose, but he's stricter. We are living in a non-trustworthy world. These are problems. This is where I'm dealing with these issues. So there is an age-old problem to solve this, basically using timeouts. If you've taken any operating systems, distributed systems, we always use timeouts to get out of trouble. So what do? Basically, I put a time lock and I say, if within 48 hours, and this is the magic that Nolan came up with, I'm going to the money, and if Bob doesn't give me the money within 48 hours, then return from the blockchain the X Bitcoins back to Alice. So now Alice puts her money, reveals the hash, waits for Bob. Bob is cooperating, then she gives the secret and he gets this money. Bob is not cooperating. Alice waits just for 48 hours. That's enough time for him to act. If he hasn't acted, she gets back her money. And Bob does the same thing. Bob, one can do the symmetric situation. Switch Alice and Bob. So Alice could be the cheater. So now Bob puts his money and he puts a timeline of 24 hours. This is the trick, and this is the beauty of this algorithm, is to try and figure out what is the connection between the timeouts, between these different protocols, between these different entities. And this is what actually Maurice Hurley did. He generalized the problem. Instead of just Alice and Bob, it could be Alice, Bob, Diana, Marty, and they all have some kind of agreement among them, and they all have to satisfy it. And I will just go quickly through this. Basically, we need to make sure that the timeline for Bob, I'm almost done, for Bob is shorter than the timeline for Alice. So basically, if Alice reveals her secret, there needs to be enough time for the secret to be put in the blockchain, for it to be potentially, we know that it's not going, not going to be any forking, etc., that the network delay, so all of these things need to be taken into consideration to figure out the delta that is involved. Okay, this is all what I would teach in the class. What we are doing research on is to try and figure out, is this a reasonable solution? And my argument is, and our argument is, that it is not a reasonable solution in the presence of failures, in the presence of denial of service, in an asynchronous system, which is the assumption that we are making about all these systems, that we don't have exact bounds on how fast every processor is executing, how fast message delays, etc. I'd like to have an asynchronous solution that tolerates failures. And for that, you need to come and take my class and learn more about all this. So I'm going to stop here, but I want to say that there are very interesting problems, and the basis for a lot of this stuff is distributed systems, database systems, security. All of these things are coming together. And there are other things that are not necessarily in computer science, but are very relevant to what we're doing. In particular, there are legal issues that are involved whenever you're studying blockchain, and lots of economic interesting problems. So it's a very exciting field because it brings in a lot of different disciplines, sub-disciplines, and interests that are very novel. Thank you. I'm going to stop.
Thank you very much, Professor. We have 5 minutes for questions, and we're going to take a 15 minutes break. So if you guys have any questions, this is the time.
Just a quick one. Do you have to be in CCS to take your class?
Yes, I have CCS students.
No, like, do you have to be a CCS? What if I'm in the College of Letters and Science by major? You can't take the class? Okay,
so it's fine with me. The problem is that the class gets filled.
Right.
So the problem, this is the problem. So if I have a room like this, once all the chairs are taken, and they give the higher priority to the computer science students, so that's where. But if you are interested and you have the background, and operating systems course is not a prerequisite, but would be very good. If you have that, come to class, and I'll try and get you in.
What is your class number?
So I do 171. Which is the distributed systems class. That's the one. For the graduate students, there's a 271.
So I'm confused about, you talked about that, like you exchange essentially like BTC for like Ethereum, right?
Say it again.
So I'm a bit confused. Like you were talking about this cross-chain transaction, right? I just wanted to clarify. So we know that like Bitcoin operates under like the unspent transaction output model, like the UTXO model, right? Essentially that means we can just, we sign it using some kind of public key if we wanted to. Like we could sign it, right, with a public key if we wanted to.
Sign it, yes.
Right,
we can
exactly.
sign it, yes.
So what you're saying is in the Ethereum smart contract, you essentially have the public key. No, you have the private key essentially. Like that's what's given in the smart contract. Is that correct? Okay.
Yes.
Yeah, I just wanted to clarify that. Okay.
Other questions? Come on, don't be shy. Yes.
Oh, thank you. I'm wondering, it's a Bitcoin a blockchain?
So Bitcoin is the cryptocurrency, and one of the main tools that it uses is a blockchain. Now, there are lots of very interesting decisions that have been made from the Bitcoin, from Nakamoto, kind of from the original conception, that affect how this blockchain is being managed.
Okay.
So, for example, a blockchain is basically, like I described, a very data structure. Now, what is the size of the block? That, in Bitcoin, is decided to be 1 megabyte. How long does it take to do, how are we going to do consensus? Now, in Ethereum, you could do something called proof of stake. In Bitcoin, you'll do proof of work. Even within the proof of work, how long does it take on average to produce the next block? So what's the difficulty of solving the puzzle, the nonce problem? So they've decided it's going to be 10 minutes, yeah? So now, am I guaranteed that there's only going to be a single chain? What if I solve the problem and you solve it at the same time? There would be forking. Bitcoin, how do we deal with forking? So, yeah, but even if we are faster, both of us could make a forking. The chain could break up. What are we going to do about it? Bitcoin decides there is an ad hoc rule which works, which is to say you're going to follow the longest chain. So there are all these kind of decisions. So blockchain, I think of it at least as a generic data structure that Bitcoin is exploiting, Ethereum is exploiting, as well as Hyperledger Fabric, etc. Hyperledger Fabric is also using a blockchain. I might design my permission blockchain with one transaction only per block. I'm going to use Byzantine fault tolerance instead of proof of work. So that's the subtle differences.
Can I say like Bitcoin is the information stored in one of the blockchain?
Say that again?
Can I regard Bitcoin as the information stored in one of the blockchain?
So the information about so the blockchain contains the history of all the transactions that have been happening in the system. So if Alice gives to Bob some money, this is put in the blockchain. If Alice had 50 Bitcoins, she gave Bob 1 Bitcoin, then she remains 49. All this is stored here. In a standard database system, we typically store the current state in the current snapshot. But here we are actually giving you the entire history, which is, if you look into the depth of a database management system, you'll find a transaction log that has all these operations also. So it's nice to understand the relationship between all of these.
We can take 2 more questions.
I was wondering what coding language you use, and also in your class and both research. And also I was wondering if you need any like machine learning knowledge or any.
No, so this is, I don't use machine learning in my classes. So for my class, and you're asking about the class. So there I build everything as though it's from scratch. So you will use Java or C, whatever language you're comfortable with. What's important is that I want you to know how to do message passing. So open socket, close socket, and TCP communication. For the class, this is what's needed. If eventually we move into, say, incorporating, I haven't done this yet, but these classes are evolving. Maybe we'll use Solarium or some kind of smart contract approach to incorporate permission blockchain. I'm still exploring this, but if we do that, we would explore it in class, so that would not be an issue. Solidity, sorry. Wait, I'm not following the question.
Yeah, I just wondering why Bitcoin is so valuable right now. Is that just because it is decentralized and there's no like authority can take charge of that?
I think there is excitement about this. I mean, there is the market excitement and the potential for it. We've been working, the computer science community has been working for years on cryptocurrencies. There's actually very important work that was done in the 90s. It did not take off. There are subtle things that Bitcoin in particular started exploring. Part of it is the large-scale distribution. Part of it is bringing different things together. So people feel this is exciting. There is also a feeling, rightly or wrongly, that maybe the real currencies are not good for everything. There are applications which are bad applications for all this stuff. There are all kinds of aspects that are pushing this. It's a difficult question, but there's the market that is driving this also. Actually, I had a slide which showed you some of the here. So there are 2,225 different cryptocurrencies. The market cap is, I can't read this, it's like $250 billion. So there is a lot of interest. It's good to be skeptical about it. I would encourage you to be skeptical about it, but there is interest. And like I said, I find from an intellectual point of view, there are very interesting challenges. Whether it will eventually end up living in the Bitcoin world or the Ethereum world or something else, that's to be seen. And I wouldn't be surprised if it's something else completely.
Would you help me understand the application example of the supply chain with the fisherman and that kind of thing? Because, so let's say the fisherman gives his fish to the logistics company that's going to ship it, and then they give it to a restaurant, right? The fisherman and the logistics company are the only ones who have a representative, like a human there at the time of transaction. So how do the other entities verify that as well?
So we'll assume that there are RFIDs and sensors that are going to help me navigate all this and suck all the information that can be stored in a system. So there has to be a human who's going, or the fish has to go in front of some machine that is going to actually physically see this thing.
I guess I'm just wondering, like, how that machine could also be tampered with. If there isn't a representative from the restaurant there seeing that, how are you still?
A good point. I agree. I don't think all this is a solved problem. I mean, this is a hypothetical, it's a real situation that we would like to solve. And we are hoping, or not me, actually, it's Hyperledger Fabric that is advocating all this, and lots of other of the permission blockchain systems that are assuming that. And yes, we have to make sure that hardware is tamper-free. And so as a result, I would go back and say we might need replication, we might need guarantees that whatever is being recorded is correct. And there has to be evidence for this. And I have another project that is really looking into exactly this problem. I have a distributed system, and I don't trust the individuals and what data they are putting in. And whenever you put a piece of data, you have to give the evidence of what you're putting in. Good question.
We gotta wrap it up, guys. Thank you very much, Professor El Abbadi. If you guys